Hi, have you ever noticed a ball ever change direction in the bowling alley? At, at first it slides, and then after a moment it starts to roll, cleanly and smoothly. But what's actually happened? Let's take the first few seconds of motion. Let's break down the hidden physics behind the classic game of bowling and how friction, torque, and angular momentum all come into play. Now let's imagine a solid ball. In our example, we can use a bowling ball, but it could be any ball. And it starts sliding across the table. So you have your table that's here, and it's sliding, and because of friction, it starts to slow down to a point where it stops sliding, and this is what we call pure rolling motion. Once it starts rolling without sliding at some point in time. Our job is to figure out how long that takes and how fast it's going when it happens, and why angular momentum is secretly constant the whole entire time. At first the ball is sliding, so kinetic friction acts in opposite direction of the motion. That friction does two things. It slides the ball down, and then it starts spinning out for linear motion. So let's start by solving the first problem. So it asked us, develop an expression for linear velocity at the center of the ball as a function of time while it's rolling down with slipping. So this is going to come back to our idea of Newton's second law, because it's slipping, we can't use our typical equations V equals RW when it comes to the rolling motion. This is not correct. Instead, we're going to have to use Newton's second law, where the sum of the forces equal to, we're going to say the sum of the forces just equals, in our example, is, let's draw a free body diagram actually so we can get a good idea. This is something you should always do. So you have your normal force that's acting upwards, and then you have gravity, which is pulling it downwards. So you have mg, and then you have your friction, which is pushing it backwards as it's rolling. So we know that the sum of the forces and its direction is just equal to the friction force, which we don't know the friction coefficient, so we're going to have to find that. But we do know that the sum of the forces is equal to acceleration times mass equals the force, and acceleration is also equal to dv dt. That's how we're going to find the velocity with respect to time. So we're going to write this as dv dt, mass equals, and then we're going to leave this as force. So at the moment, we're going to have to figure out, how do we find this friction force? Because we have multiple unknowns, we have to find some way to substitute it out. And luckily we have this idea of torque, which will give us two equations to substitute it out. So the sum of torques is equal to, let's draw another picture to give us an idea. You always want to draw a diagram. So you have your center, and then we know that the ball has a radius going downwards. This is going to be our lever arm, and then the friction is going at a 90-degree angle. If you remember, torque is equal to a force times a radius, the sign in between, which is also the cross product of the two. Alright, so we know that we're going to have our static friction, or no, this is kinetic friction since we're sliding, is times the radius of the ball, which is capital R. And then we know that the sum of the friction of the torque is equal to the angular acceleration times the inertia of the ball. And the problem, it states that the inertia of the ball is equal to, as recalled, 2 over 5 times its mass, radius squared. Pretty often you always have a mass times a radius squared for inertia when it comes to angular motion. So now we gotta substitute these out. We have to substitute our force out somehow here. We know, actually, we do know our friction force in our problem. It states that it's the coefficient of sliding force. So I guess I'm solving both at once. So we're going to have this right here, and then we're going to solve for our velocity before we finish here with respect to time. So we're going to have dv m equals the sliding friction times, if you go back to our full body diagram, the normal force is equal to the gravity, which is going to be mg, which will means the mass cross out. And now we got to take the integral to find our velocity with respect to time. Remember, it starts at initial velocity, so we're going to go to v naught to v for our velocities, and then for our time it goes from time 0 to t in our problem. So that's going to give us this right here, coefficient of kinetic energy times g, and then dt. This will give us v minus v naught equals, and then we're going to have just the t times the at the end here. Now we have velocity with respect to time. We'll just get velocity on its own, which is equal to v naught. And then we also got to remember that this friction that's acting on the ball is opposite direction where it's going, so it's going to be a negative. So we're going to add a negative to all our frictions here as the following. And then we're going to have our final solution is right here. This will be the linear velocity as the center of the ball as a function of time. Well, the ball is slipping. There's no non-slipping motion happening in our example here. So we're gonna save this for later for problem 3. So right now I'm just gonna circle this and then save it for later. Now I'm gonna erase what we have here so I can move on to the next part. And then we're going to move this up so we can save it for problem 3. Alright, now let's solve for the angular velocity of our ball as it's traveling, well, it's slipping as it travels. So we're going to have the sum of the torques equals the friction kinetic times its radius. Now we just need to substitute the angular acceleration and then the inertia out so we can know what it's equal, so we can find our angular velocity. So we know this angular acceleration is equal to the d, like a small part of our angular velocity, and then over dt, and then our i's or inertia is equal to 2 over 5 mass times radius squared, and we know that the friction is equal to the friction coefficient of kinetic energy, and then we know from our free body diagram that the force, or the normal force, is equal to mg. This will cross out our masses in our problem, and then will leave us with the integral of du from 0 to u, since the ball is not rolling initially, and then it's going to be set to equal to 5 over 2, and then we're going to have a another. We're gonna have our friction coefficient K times G, and then I think we forgot the R on this end here. That's what I was thinking about. So we have one R, which is gonna go on the bottom. So now we're gonna take the integral of both sides. This is gonna go from 0 to t. This will give us the angular velocity with respect to time is equal to 5 over 2 times the friction coefficient of kinetic energy, g, and then we're going to write r on the bottom times our time that we're looking for. So now let's circle this with a green box so we can solve our third problem and second to last. Our last question will be more of a theoretical question. So now our next question asked us for today, it says, determine the time at which the ball rolls without slipping. So at some point as this ball is sliding to the right, the ball slows down to a point where the ball stops sliding. And it asks us what time will this stop rolling, which is pretty important. So it's going to be whenever this statement's true. So if we remember from before, we have the velocity is equal to the radius times the angular velocity, which makes sense, right? So now we notice we can just set them equal and look for time. So we're gonna have v naught and minus our friction coefficient of g times our time that we're looking for. This is when it's true, is when it stops sliding, which is one of the best ways to solve it. Most efficient ways, since we're already working towards this way. That combines the idea of transitional and rotational kinetic energy. And then we have just this left here. Now we need to get the times on both sides so we can get those out of the equation. So we're going to have a kinetic energy or friction coefficient here, gt. We're not having this t here anymore. And then it's going to be plus radius, 5 over 2 radius. And then our friction coefficient over the gravity divided by its radius. So the radiuses look like they cancel out here. So we're going to eliminate our radiuses and then our times on the outside. Now we're going to divide the rest of it with what we have. So we're going to have a v naught divided by, so we're going to put this on the side since it's just a constant. And then we're going to have our, oh yeah, we have to also combine these values because we have similar values here. So if you look here, we have our friction coefficient times gravity, friction coefficient times gravity. So we can actually combine these two numbers here. So we're going to change colors again. So we're going to v naught is equal to, it's going to give us 7 over 2 the friction coefficient times our gravity, and then times time. Now we find our final solution is going to be 2 over 7 times v naught over our friction coefficient of kinetic times the gravities is equal to the time. So this will be the equation when the ball stops rolling and stops sliding and it starts like rolling without sliding. The exact time. So it's whenever the initial velocity divided by our gravity divided by our friction coefficient times 2 divided by 7. That's our exact time given our inputs. So when the ball is struck, it acquires angular momentum about the fixed point P on the surface on the table. During this subcentric motion of the angular momentum at about point P remains constant despite frictional force. Explain why is this so? So it's asking us about the angular momentum at the point P. So we're going to redraw our point P so we can know where it's at. So P is going to be right here. And we're going to have a P that shows where it's going to be. Okay. So it asks, why is the angular momentum not changed at this point? The reason this is so is because the friction is acting on the point of axis if we're using P as our axis for angular momentum, and so it doesn't change. The only thing that has a torque on this point P is our gravity, which is mass times the radius of the ball, which never changes throughout the progression as it starts to slow down. So that's why the angular momentum can be totally different depending on where you put it. If you place the angular momentum at the center, it would actually decrease as the ball slows down, since the friction force is slowing it down. And then we have our mass times gravity, which is on the axis, so it doesn't produce torque. And thank you for watching this video today. And don't forget to like and subscribe to help you out.